Welcome back. In the previous week, you have learned how to design a complete PV system. Therefore, you know a lot of technical aspects about the modeling of a PV system, but this is not enough to really determine if a PV system is viable in the real world. It is time to talk about the financial aspects of the PV system. In this video, you will learn about the economical metrics relevant to PV systems. You will be able to answer questions like, how do we compare the costs of different electricity generation technologies? How do we estimate the effective costs of energy? The learning objectives of this video are that you understand some crucial economic metrics like the concept of levelized cost of energy, or LCOE, which determines the cost competitiveness of the various renewable and non-renewable technologies. Then other metrics will be introduced like the net present value NPV or the payback period. Finally, we will discuss the factors that affect the cost price of a PV system. Let us start by defining the levelized cost of electricity, or LCOE. The LCOE is defined as the cost per kilowatt hour of electricity generated by a certain energy system. It is generally used to compare the lifetime cost of project based on the various power sources. For the levelized costs, the overall cost of an energy plant during its useful lifetime are calculated. Then the overall energy production of the plant over its lifetime is determined. Using these two numbers, we can then figure out the LCOE of a given energy system. The calculation of the LCOE can get quite complex depending on the number of parameters taken into consideration. In simple terms, if we know the annual yield of the PV system over its useful lifetime and the system cost, the LCOE, can be determined according to the shown formula. Here IT is the investment expenditures over a year T. So if a lifetime of the system is 25 years, we take the invested value in the beginning and divide it by 25 if it was paid for all at once. The operational and maintenance costs over the year T are denoted by MT in the equation. FT denotes the fuel expenditures in the year T. And of course, for PV, fuel costs are zero since we get sun rays for free. ET is the AC yield generated in the year T, and R is the discount rate, which is a factor used to discount future costs and translate them into the present value. Finally, N is the financial lifetime of the system. The lifetime of a PV system is around 25 years. Let us now look at the LCOE for various utility scale generation technologies. Note that this is just an example. LCOEs might be different from region to region as the climate conditions, the policies, the regulations, the local capacity factors of the electricity generation technologies, and local markets might also be different from region to region. The LCOE consists out of different cost components. Here we give an example. The levelized capital cost in blue are calculated for the technologies under study. Here we look at large-scale utility of PV on land, onshore wind energy, combined cycle gas turbine plants, and a nuclear plant. Other cost components are the property tax and the insurance, here shown in the dark green, the fixed operational and maintenance costs, here shown in the light green. The transmission costs are shown here in the red, which translates to the cost incurred to access the transmission lines. Additional costs are the fixed integration costs, here shown in black, the fixed fuel costs, here shown in yellow, and the variable operational and maintenance costs, which is here referred to as the variable fuel cost, shown in orange. The advantage of renewable energy sources are the zero variable operational and maintenance costs due to the absence of fuel costs, which to the contrary are present in fossil fuel and nuclear generation technologies. Hence, finally, we can see that PV technology is getting increasingly competitive and even cheaper compared to fossil fuels, with levelized costs for PV of around $40 per megawatt hour. Note that the LCOE might be different from place to place. This is shown in this graph adapted from the IRENA Renewable Cost Database. It shows the LCOE of large-scale utility projects around the world. The size of the circle represents the size of the generation power of the large-scale utility system established. It shows the LCOE in 2010 for various technologies and in 2021 for various technologies. It shows that within these 11 years, photovoltaics, shown here in yellow, has developed to become, together with hydroelectricity and onshore wind, the cheapest technologies around to generate electricity. In many regions in the world, PV is already the cheapest form to generate electricity. The next metric that I want to introduce is the net present value, or NPV. The NPV is defined as the current monetary value of the profit made over the investment lifetime. It is used to determine whether an investment is convenient or not in terms of economic profits. For the net present value, the cost and the revenues of a power plant are added or subtracted over its lifetime, as depicted in this formula. The term C0, C0, represents the initial investment costs, which are subtracted to the NPV value. Then, for every year T of operation, the annual revenues RT are added, and the operational and the expenditures CT are subtracted to the equation. Then R is the discount rate, which is used to discount future costs and translate them into the present value, as seen in the LCOE formula. Finally, N is the financial time of the calculation from the moment when the initial investment is made until the last year of operation. Since NPV is just an algebraic sum between the cost and the revenues that occur during the lifetime of a power plant, it can be used to determine whether an investment is convenient or not. If the NPV is positive, it means that the revenues are higher than the cost, and therefore the investment is convenient. On the other hand, if the NPV is negative, it means that the revenues are lower than the cost, and therefore the investment is not convenient. Suppose now that the NPV value is positive, so the revenues will be higher than the cost at the end of the lifetime, and therefore the investment is convenient. There will be a moment when the total revenues are equal to the costs. In other words, there's a moment when the net present value becomes equal to zero. Such a moment is called discounted payback period, and it's usually measured in years. It is defined as the time taken to earn back the investment. Sometimes you will also hear about payback period, which is a simplification of the previous formula, since the future value of money is neglected. Therefore, the interest is set equal to zero in this case, as the formula appears as shown in this slide. We can understand better the concept of payback period with a simple example. Let's say, for instance, a household has installed a PV system of 1 kilowatt peak at an investment cost of €4,000. The family usually electricity consumption is such that on an average it incurs an electricity bill of €2,000 per year, and after the installation of the PV system, roughly €800 worth of electricity is consumed by the family, which is provided for by the PV system. In this graph we see a straight line denoting the fixed investment cost in the beginning. As the family consumes more of the clean power produced by the PV system, it offsets the electricity bill accordingly. In this example, the amount saved is €800 per year. In other words, the family earns a return of €800 per year on the PV system investment. As the years progress, the savings accumulate, and there comes a point in time when the accumulated savings are greater than the original investment. The period of time elapsed until that point is called the payback period or the payback time. In this case, the family's PV system has a payback period of 5 years. Another aspect that controls demand is the cost price of the PV technology of the PV system. How does the cost price of the electricity generated by a PV system compare to the electricity delivered by your energy company? To answer this, we have to look towards the learning curves. The learning curve is the graph which shows how the cost price, or in this case the sale price, is dropping in time. In time, the industry gets more experience. Like progress in technology provides for better PV modules with higher efficiencies. This experience results in better and faster processing, leading to higher production yields. Upscaling of the production leads to lower cost of the source materials. Learning curves usually show an exponential decreasing cost price in time until the technology or the product is fully developed. In this graph, we have the average global sale prices of a PV module in inflation-adjusted dollars per watt peak. The sales price is plotted against the cumulative production in gigawatt peak. Important to note is that the sale prices, discounting some fluctuation, follow a largely exponential decay. Currently, at the date of the recording of this video lecture, the average retail prices of PV modules is around 20 cents per watt peak. However, be aware that if you are watching this video in a year later than 2023, this number might be already obsolete, outdated. Now we will see how the cost price of a PV system is not only determined by the cost of the module. The red dots show the decrease in the cost price of a complete PV system. Here with typical sizes of 10 kilowatt up to 100 kilowatt peak, as an example in the German market. As you can see, in the early days of the PV technology, the system price was dominated by the module price. In the current situation, however, the contribution of the non-modular components, also referred to as the balance of system cost, start to play the most dominant role. By the balance of systems, we consider components like the racking, the wiring, the inverter, the batteries for the standalone systems, as discussed earlier in this MOOC. Maintenance costs, such as cleaning and repair, are also needed to be considered. The difference between the red and the blue line corresponds to the balance of system as shown in the green curve. The green curve represents the learning curve of the balance of systems. This learning curve is not dropping as fast as the module price. This means that nowadays the reduction of the cost price of a PV system will be mainly limited by the cost price of the non-modular component, the balance of systems. Modules with higher conversion efficiencies means higher yields per area. While the balance of systems per area is the same, the cost price per watt peak of the balance of system will consequently be lower for modules with higher conversion efficiencies. In this video, you were introduced to some important economic metrics like the concept of the levelized cost of energy, or LCOE, which determines the cost competitiveness of the various renewables and non-renewable technologies. You also were introduced to the net present value, which is defined as the current monetary value of the profit made over the investment lifetime. We also discussed the payback period of a system. Finally, we have discussed the cost price of a PV system, which includes the modules and balance of systems. In the next video, we will look in more detail to the various electricity markets which are around. So, see you back in the next video.